recording so we can get started. Hello, welcome to Handmade Hero. We had a little bit of a rowdy pre-stream, it's true. I was kind of going off on how I thought that gamers in the gaming press had done a remarkably good job, actually, at creating a positive market for games, and I got very excited saying how I think people don't appreciate that enough and that they should. And so I'm a little worked up, but that's okay. So let's go ahead and get things back to graphics, which is our topic for today. We are here on day 93, so if you would like to follow along at home and you have pre-ordered the game on handmadehero.org, please unzip day 92 is source code, and that is where I am today. All right, so where did we leave off, people? I hope you remember, because it was a lot of fun yesterday. We left off with the first time we actually started filling solid shapes that could be arbitrarily rotated and scaled. And so what we need to do now to complete sort of our push forwards into adding more graphics features so we can have a real renderer is we would like to start filling these shapes. And I guess I should correct that. That was, again, people egging me on in the post stream. People are always like, do this, do that. And then I kind of feel like, oh, well, maybe we should do that, right? We were not going to support that. We are only supposed to be supporting rectilinear blitz here. So there we go. So anyway, what we want to be able to do is we want to be able to support rotated and scaled and potentially non-uniformly scaled. So we'd like to be able to scale differently in different directions as well. So, you know, for example, we may want to be able to make it so that, you know, things can be oblong as we blitz them, right? But that's it. We're not going to support skewing or any of that sort of stuff because we don't really need it. So we're just going to concentrate on this kind of a thing. So we want to be able to do exactly what we're doing right here. We did the work for it yesterday where we can fill a shape with a solid color. What we want to do now is we want to see if we can move from that to actually filling it with an image, right? So what we want to do is we want to start doing texture mapping so that we can scale and rotate our sprites. So like, for example, this head here or this torso, we want to be able to do that so that we can basically map any image that we want onto one of these excuse me, one of these rotated and scaled quadrilaterals, right? And so what we're going to do is talk about that on the blackboard today. I don't know how far we'll get, but we'll talk about that on the blackboard, and then we will start implementing it. And then next week, we will pick up wherever we leave off. Okay, so there we go. That's where we're at. What I would like to do is I would like to go ahead and start us off by simply saying, before we go to the blackboard, we're going to have to start passing what we want, you know, in our little render entity coordinate system here, which is like a little test bed. We're going to have to start passing down some image that we want to be the texture, right? Like whatever that texture is that we're going to map, we need to be able to pass that texture down. And so what we're going to do is we're going to expand our notion here of coordinate system, right? We've got it in here where we're passing a bunch of stuff to it. What we want to do is after that color, and then I guess I'll sort of make this a little easier to read there. After that color, we want to pass some texture that we can use to fill things. And so we've got, you know, we've got a situation where we had in our game state structure a bunch of things loaded. So maybe we'll just grab the tree or something and say that the tree is going to be what we draw, right? And so if we go into our thing here and say game state tree is what we draw, then in our render group, when we push on one of these coordinate systems, we can pass a loaded bitmap, which is going to be the texture, and then we'll just store that onto the render state, and we'll go, all right, you know, that's the texture that we're going to fill this quadrilateral with, right? And so, you know, we've got that pushed on there now, and the tree is in there, but we don't actually have it filling. So that's going to be what we're going to talk about today, is how do we start getting that in there. And when we do our draw rectangle slowly call, which is this right here, we're going to want to pass that as well, right? And our draw rectangle slowly call will now take that loaded bitmap as its parameter. Okay, so if you remember, the way we were doing this is we had our edge equations, and the edge equations were telling us whether or not we were inside the shape that we wanted to fill, and that this test right here, which said they all have to be negative in order for us to be inside, that was what would tell us whether we should take the pixel that we're on and write to it with the color that we had, or whether we should just let it pass through, right? And we also had another mode we could switch to here where we do if we switch to the if0, where we could just see all of the pixels we were visiting, right? And we haven't done anything smart to do the culling here, so we're literally just doing the bounding box of those points, sort of an axis-aligned bounding box of those points. But that still speeds it up quite a bit compared to doing the whole screen, as we saw yesterday. So it's a worthy thing to do the optimization, but in the future we'll probably have to do something a little smarter so that we aren't considering so many pixels that are nowhere near the actual interior, as the case is when it sort of gets a little bigger there, certainly. So anyway, that's what we're doing at the moment. And we've got that going. So what we need to do now, right? We know that we don't have to change any of what we're doing for filling pixels because that's all the same. All we really need to do is this color 32 here. This color 32 is not useful anymore, right? That's the color that was passed in, and that's not what we want. We want to be able to put in place of that color 32, a color that we read from that texture that got passed in. Right? And so let's talk a little bit on the blackboard about how that's going to go. And what I'm going to do here is I'm not going to try and lead anything. I try to do this a lot on the stream, like I've said multiple times. I'm not going to try to lead us into the correct answer. What I'm going to do is show you how I would go about creating a solution to the problem that we have. And then sort of later on, we'll kind of revisit and talk about solutions that other people have come up with that are probably better than the one that we'll come up with, because this is the sort of topic that's been studied by many, many people over many, many years. And so the thing that we'd come up with first is probably not the best thing. But I think that it's good for me to show you how I work through problems all the time. And so even though we're probably not going to arrive at the exact answer that we'll use eventually for efficiency and all sorts of other reasons, right? I think it's beneficial for us to show how we can work through things from first principles and come up with an answer, because that's always the start of solving new problems. And yeah, maybe it takes 10, 20 years of people cranking on it to come up with the final best solutions to things, but that's not necessarily what we're trying to teach on this stream, right? You can always go read a research paper to find out what the current status of something is, but when you're tackling a problem that hasn't had a solution yet, the important thing to know is how to do that, and so that's what we always try to do. So I'm going to sort of say, I'm going to show you how to think about this problem and start to try to attack it, and we're just going to go with what comes out of that analysis. So what we have, right, is we've talked about this many times now. We've got our coordinates laid out here. We have our y-axis and our x-axis, right? And these are scaled. And basically what we're saying is that we're drawing a rectangle that looks like this, right? So by the time we get to the x, this is our origin. By the time we've moved out by the y-axis on our origin, we've come to the end of the bitmap in that direction. And by the time we moved by the x-axis from the origin, we've come to the bitmap's end in that direction, right? So what we would like to do is we would like to take some regular rectangular grid of pixels, right? This is our texture over here, right? This is our texture. What we would like to do is take a regular grid of pixels, and we'd like to figure out at any point in here where, what pixel would map into there. And we can sort of imagine how, that looks just in our head. We can imagine taking this grid and, aligning it in here, right? And we can already start to see, like, it would be pretty obvious to us if we were just asked to do this. Well, we just kind of move and sort of rotate it into place and squish it till it fit. And then, here's A, here's B, here's C, right? There it is, A, B, C. And, those things would kind of line up. And, I should actually probably point out that since we're in a bottom-centered coordinate system, it'd really be this way, right? A, B, C, like so, right? So what we'd like to do is say that, well, we've got pixels, right? And we know how to address this thing because we've been using these bitmaps a ton. We know that we can address these by an x and y that are in pixel coordinates, right? But it's confusing because we also have an x and y over here that's the pixel grid that's actually the thing that we're filling, right? So there's like two grids on top of each other, right? There's the xy grid that's the pixels we're filling, and then there's this other thing over here. So what we're going to do is we're going to try and use standard nomenclature here, which is UV, sometimes ST, depends on the circumstances and what space you're talking about. But oftentimes what people will talk about is they'll talk about UV coordinates for a texture map. And we can also think about those UV coordinates in two different ways, right? And so I'm just going to tell you what those are briefly, and so we can use the right nomenclature as we sort of solve for this, because that'll make it a little easier to understand when we talk about other solutions to this problem a little later on. So again, I'm not introducing any solutions here. I'm not trying to lead us. I'm just going to introduce the terms properly so that when I start saying something, we can use them. So typically the way that people talk about indexing into these bitmaps is they talk about UV coordinates meaning sort of the U is in the X direction, the V is in the Y direction, and they actually range from 0 to 1. Okay? So normally when we were talking about looking up in that texture, right, we were talking about having sort of X range from 0 to the width, right? And actually the width minus 1 would be the last pixel. All right? And when we were doing Y, we were talking about it going from 0 to the height minus 1, right? And so that's how we know how to look up into this bitmap. And so this is sort of the U and V paradigm's a little weird for us, but you know, we've worked with this so much before in Handmade Hero, things like this. We can already see exactly how we would do this, right? We already saw this sort of mapping from 0 to 1 to do mapping from 0 to 255, right? When we were doing colors, right? All we do is we take the 0, 1 and we multiply it by whatever that range is, right? So we just take, if we have some value here that's sort of our normalized value, it's the 0 to 1 value. When we want our sort of expanded value, right, we just take whatever that is, whatever that maximum value is, and it's just n times the max, right? Because then when it's 0, it's still 0, and when it's 1, it's the maximum value, and everywhere in between, it's whatever the linear proportion is of it, right? So it's pretty free for us to talk about things in terms of UV coordinates, because we always know that these are basically interchangeable. So we can say UV to talk about something in a texture, or we could say like the texture's X and the texture's Y, which would be like more like these values. And really, we don't have to care too much about which one we're talking about, because we know that it's, while it may be an efficiency concern later that we need to think about, in terms of conceptually, we know how to address a texture in either way, right? We would know how to get it either way, because if we have these, then it's just the same pixel lookups we've been doing. If we have these, we just first multiply them by whatever the width minus 1 is and the height minus 1 to get out tx and ty values, and then we're done, right? So real straightforward stuff. So the question is, right, how do we produce some U and V values, right, that tell us where in the texture we are at any given time? And if I draw this diagram a little more cleanly, right, let me draw it a little more cleanly here. So I'm going to draw the pixel grid that we're on, right, like so. So this is the pixel grid that we're on. And this is the screen, right, at this moment. This is what we're drawing to, okay? And now I'm going to draw in our sort of coordinate system, right, that we're actually filling, or at least I'm going to try to, like so. There we go. So here's that y-axis pointing out here. Here's that origin down here. And here is our x-axis here, right? And so we now know that this is essentially what we are filling, right? We are filling this region. Oops. So what we know is we're going to have a bunch of pixels who fall inside these lines, right? Like this, at least this pixel, this pixel, this pixel, this pixel, this pixel, this pixel, right? They fall inside the lines, right? So these individual pixels that fall inside the lines, we know that we are going to fill them in, and currently we're filling them with a solid color. So what we want to do is say, for one of these pixels, what would be the way to look up into the texture to figure out what color we actually should put there, right? And what's interesting about this is we actually have a pretty straightforward way of knowing what that is, right? Because all it would be is, all we'd have to do if we wanted to solve that is just figure out what proportion of the x-axis it took to get there and what proportion of the y-axis it took to get there, right? Because we already know that if we started at the origin and started walking out on the y-axis, right? If we walked out 1 units along the y-axis, we'd be here. Because however long it is, that's how far we would step. We'd step 1 times the y-axis, right? And so what we really want to know is how far along the y-axis this actually was, because however far along the y-axis that was, that is how that is the value, right? Because again, if we were to use this normalized thing here where we're saying that u ranges from 0 to 1 and v ranges from 0 to 1, then just a v that said how far from 0 to 1 we were along this axis would be the correct answer. And similarly, mapped onto the x-axis, right, that would be our u. So really, this value here, normalized for the length of the y-axis, would be our v, and this length here, normalized for the length of the y-axis, would be our u. See what I'm saying? So let's take a quick look at what's going to happen here, right? So if we were to take a given pixel position, right? So there's our given pixel position, right? That's P. If we're to take that given pixel position, what will happen if we dot it onto the y-axis, right? Because remember, the dot product is what measures things against it. So if I want to do this projection, I know that if I was to do, so let's in fact also say that P, instead of here, let's pre-say that we've subtracted the origin. So it's actually this vector here, right? We could call that something else. I'm not sure what we would call it. Let's call it, instead of P, let's call that our D or something, right? So that's D. So if I were to take D and dot it against the y-axis, so I've got, oops, D dot y, right? What does that equal? Well, I hope you remember this by now because we say it so many times. It's the length of D, right, times the length of y times the cosine of the angle between them, right? That's what that actually equals, right? And so, excuse me. And so what I'm going to get here is I'm going to get whatever this value actually would be, but with a bunch of lengths inside it, right? I've got a bunch of lengths in there that I don't actually want, because I don't know what the length of D is, and I don't know what the length of Y is, and really what I wanted is I want a number that goes from 0 to 1 that says how far along this thing it went, right? And so it's an issue, right? There's a problem here. It's not something that I could use directly. So let's say, temporarily, right, that I were to normalize these vectors, right? So I were to take them and I were to normalize them so I know that these lengths are 1 and 1, right? So I would to say like, okay, D and the y-axis are now just going to be vectors, and all I'm going to do is look at the cosine in between them, right? So all I'm going to do is I'm going to try and figure out what this length is if the y-axis was equal to 1, right? Was already unit length. Okay, and so if I did that, right, that would just be sort of the normalized D. I don't know what we'll call that. We can call that D normalized, right, and Y normalized. If I did that, then I would know that I would just have that cosine term purely because both of these are equal to 1 and they would go away, right? And so let's think about that for a second. Does that actually give us what we the value that we actually want? Right? Does that actually give us the v coordinate, if you will, or the u coordinate if we were to do it for the x-axis? Does that actually give us what we want? And so let's think about that. Excuse me. So another way to go about thinking about this problem was if we were to, if we were to normalize just the axis but leave the point the same length, right? So let's say I was going to do D transpose Y normalized, right? That would give me the length of D times the cosine of theta, and it would take this out of the equation, right? This value would tell me exactly the location of where this was along that y-axis in absolute distance, in actual pixel distance, right? So in order to figure out how far along the y-axis we were, the first thing we would do with that, right, is to divide it by the total length we could have gone, which was that length to begin with, right? So if you think about it, right, what we really wanted to do here is we sort of wanted to divide by the length of y twice, if that makes any sense, right? Like what we wanted to do was we wanted to say, okay, we wish we had y normalized because this is the value that comes out. This value here doesn't really help us, it doesn't look like, because this value is divided by the length of d and the length of y. But it looks like what we would actually want to figure out this point, right, is we'd want to figure out the length, excuse me, we'd want to figure out that cosine term divided by the squared length of y, if that makes sense, divided by that y twice. And so let's do that one more time just so we can kind of see what's going on there and make it a little clearer, right? So I'm going to draw it this way, right? So here's the measurement axis, right? Here's the measurement axis. And this could be y or x, right? And so what I'm going to say ahead of time is that this is unit length, right? So the length of this axis is going to be equal to 1, right? And then I know I've got some length, right? I don't know how long it is, but I know I've got some length. That's the length of my quadrilateral, right? So that's the length of this thing, right? So let's say, let's call this axis, let's say that A is the axis, right? So the length of A is 1, right? And then we've got another length, let's call that L, right? And L is going to equal, you know, however long the texture is. So this is the actual, or sorry, the quadrilateral. So this is our actual quadrilateral length, right? So now if we have some point, no matter where that point is, right? Here's our point P. And we project it onto this axis, right? We know we can do that by saying that that is the point. And again, this is the point. I shouldn't do that. We'll do D, right? So it's the minus the origin, right? So D is always equal to P minus origin, right? There we go. So if I take that D and I transpose it by A, now I get the length of D cosine theta. And that's what I actually want to measure against. That tells me how far in actual pixel space I am over. But now I want to turn that into a uniform coordinate that goes from 0 to 1. So I'm going to divide by that L, right? And again, you can see that again. So that L, that is just how long the axis would have been, right? That L is just the length that A would have been if I'd let it go the whole way, right? So you can kind of see where I'm getting at that. So really, it looks to me like what we want is we want D transpose the actual axis. So whatever the actual axis, the original version was before normalization. So like the y-axis, right? We want to do that to produce length of D, right? Length of y cosine theta. When we do that, we can then just divide that axis after we're done with it. We can divide that by its length twice, right? So whatever this length is, we do that twice. Divide and divide. And that produces this equation up here, right? It cancels the y once and then still leaves that length on the underside. So that looks like the correct value to me. Again, I just worked that through. I have no preconceived notion of what the answer actually should be. That's just what I thought it should be based on what we said. I may have made a math mistake or two along the way, but that's the first thing that I would like to try, right? And so now let's talk about how to get that. So in here, when we actually do this pixel P minus origin, right, you can notice that if I actually were to refactor this, and let's just do that. I said we were going to do simpler origin. We didn't do it yet. But if I were to refactor this by distributing this negative, right, if I distribute this negative, that would essentially distribute out and make this negative here and negative here, right? Again, distribute the negative, 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 distribute the negative, 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 right? And if I recompile that, you see that we didn't change anything, right? So I just distribute that negative out. What that allows me to do, too, is introduce that value that I just said, D, right? So if I go ahead and take my pixel P minus origin and make that D, you can see that these are just all the same thing, right? We still haven't simplified that, but, you know, same basic idea. Oops, that goes up there, right? But if I do that now, same exact thing. And there's that D value that I actually wanted. We were already kind of using it to compute the thing. So now if I want to compute what the texture coordinates are, right, I want to compute that U and that V, right? So if I want to compute the U coordinate, well, first of all, I suppose we should say we don't need to do this unless we're actually inside, right? Since we're already doing a test, we might as well not do the texture lookup unless we're inside. So what we want to do is say, okay, we've got that U value, and what I said that was going to be is I said that was going to be the dot product, right? So we're going to do the dot product of whichever axis we're trying to measure on. So for the U, we're doing the x-axis, right? And we want to do that D times the x-axis, right? Then what we want to do is we want to multiply that by the length of the x-axis inverted, right? Squared, sorry. Right? So I want to divide, which means I'll pre-do a 1 over for it. I want to divide by that x-axis length, right? Squared. So that's what I actually want to do. Does that make sense? And similarly for the V, I would do the exact opposite, do the exact same thing, but for the y-axis, right? And that should produce my U and my V, right? Similarly, I could just think of this as a vector, the UV vector, right? And that's just composing these two together so that when we pass it to a texture sampling function, we could do that, right? If that makes sense. So there we go. All right. So let's go ahead and pre-compute these values because we need to, right? So when we get that x-axis and that y-axis, if we want to do the inverse of the length squared, we just do length squared x-axis, right? That's just the inverse of that, and the y, right? So there's 1 over in both cases, like so. And then we're computing our u and v's, at least in theory. We are computing them. And of course, we haven't actually done any lookups yet, so that's fine. So now all we would need to do is actually look up the u and v inside the texture. And so I'm going to do a function for that now. Or I guess I don't really need to do a function. I can just write it in place. That's fine. So we've got that texture, right? We've got the texture, and it's one of those loaded textures, right? And so I believe, is that in here? Where is loaded bitmap defined? I don't even know. Loaded bitmap, there it is. Okay. So what I want to do is I want to look up into here to try and get whatever the actual value is that the pixel should be to replace color 32, right? So if I'm going to do that, I'm going to go ahead and say color 32 equals some lookup into the texture. I'm going to first need xy coordinates, right? So what I can do there is say, all right, the x coordinate is going to be equal to the u. And in fact, I guess this would make it a good reason to have not bothered to wrap them up, at least not at the moment. So I'll go back to using it just like this for now. There we go. There's our u and v, like so. So that u coordinate, I just need to multiply that by however big this texture actually is, right? So whatever the texture is, I just need to multiply it by the width. And of course, I need to subtract 1 from that width first, because I need to make sure that the final, if the value is actually 1, I want to end on that actual final texel, right? I want to end on that final piece of that bitmap, right? So what I want to do here is just say, all right, take whatever that u proportion is. And furthermore, I could do an assert in here for just for the time being, say that these are within legal range. Since we're doing some debugging here, we want to make sure that that's the case, right? So what we'd like to do is do that. And once I do this as well, one thing we might want to do, again, is round this properly. So we might want to do something like that, right? Where we go ahead and sort of, oops, I did that right. Didn't do that right at all. There we go. So texture width times u. No, that's correct. Never mind. We'll deal with the rounding in a second. All right, there we go. Okay. So when we do this lookup, we're multiplying by the u. That's going to get us all the way there. And then this is a truncation. So what I was sort of saying was, well, once we do that, what I'd like to do is add the 0.5 in so that we will round in either direction depending on which one we got. Okay. I'm just trying to think if that ever gives me. No, that will never produce an out of bounds. So okay, so we're good, at least for now. And so the same exact thing is true for the height, right? No difference there, exact same thing. And we've got the u and v tests in here just to see whether we're fetching outside at all. And let's go ahead and compile that and just see if we, so we're, at the moment, we're never computing a u and v that's out of range, so that's a good thing. And similarly, we could assert that our x is greater than or equal to 0 and less than, or no, just less than the texture width, right? So that we know we'd never be fetching out of bounds, like so. Oops, that's width. My bad. I meant height. There we go. So now, yeah, we're still not fetching out of bounds, so that's good. Everyone's happy. And so now what I'd like to do is go ahead and actually do that lookup, right? Which is pretty easy for us to do. We know exactly how to do this. We've done it a million times. Well, a million's a little bit much potentially, but you know, we've done it many times. Let's put it that way. We start with a pointer to the base, right? We then want to walk along the rows as far as we need to get to the correct row. So that's just going to be whatever the y coordinate is times the pitch. And then we need to walk over, right, by however many we have width-wise. And that's just going to be however big a pixel is, right, which we know the pixels are 4 bytes per, right? And so that will give us the correct pixel that we're trying to access there. And in fact, I'll do it this way. This is like our texel. This is the texture that we were looking for, right? Makes sense. And then what I want to do is I basically just read that in. And so this is the texel value. I guess I'll call this texel pointer, right? whatever the texel pointer is, I just want to treat it like it was a 32-bit value at that location. I want to read out, that's the RGB and the A. I'm just going to read that out, and then we'll store it exactly, right? Like so. And so, hey, guess what? We've got texture mapping, right? And there's our tree. And as you can see, very simple, worked the first time, nothing particularly fancy going on there. We can look at it a little more closely. And you know, that's texture mapping in a nutshell, right? We can add alpha blending to this routine if we want to still do the alpha cutout. So that alpha blending that we were doing before, you know, we can make that happen. In fact, we probably should. Wow, that took almost no time at all, but there you go. All right. We haven't handled a lot of the sort of finickier stuff, and we haven't done any optimization, so I suppose that's the more fancy stuff. But ladies and gentlemen, texture mapping, not very difficult. So that's kind of the basics of it. Let me go ahead and add in that sort of that alpha-ness to it, right? We have the alpha stuff happening here. So what I'm going to do for now is I'll just go ahead and grab this in here, what we were doing before for the alpha. And so if I want to do that when we're in this routine, right, let's go ahead and paste that in there so that we can kind of, so that we can do that editing. So we don't have this anymore, and we don't have that. We've just got the pixel right going on here. And so in here, you know, after I do that texel lookup, what I need to do is I need to go ahead and make sure that we're reading from the right places, right? So there's the pixel that's coming in. There it is. We'll do that alpha stuff on it, right? Then we've got the texel that's coming in, and that texel is our source now, right? Like so. And and I don't know if that's it. Let's see. Legal indirection of the texel. Oh, right. We don't need to do star on that. It's already been dereferenced. So now all we need is that alpha that's coming in, so the alpha that's going to modulate this. And I'll just go ahead and say that that's actually, because that C alpha, we're getting a color passed in that does have an alpha value, right? It's this one right here. And so what we'll do is we'll say color dot A right there. That's our modified alpha, right? And that's color dot A. Oops. Color dot A. Color dot A, right? And so now we're correctly doing the alpha composite too, which means that we have, you know, the texture mapping working with all the same features that we previously had working in our bitmaps, and that's pretty awesome as well. And so I'm trying to think if we should quit while we're ahead here, because the next sort of stuff that we'd be getting into would be a little fancy. But yeah, I mean, let's just do it. All right, so what we're going to do next is, first of all, we need to slow this down, and we need to do some stuff to kind of get ourselves in position to understand the reasons why we might need to do some of the things that we're about to do. So let's clean this up, and let's stop getting fancy in this place so we can get fancy in other places. So for now, I'm going to say let's keep this thing fairly uniformly sized for the... What just happened? I have no idea. So we have produced a hue that is outside our precision. Well, you know, it's bound to happen. These kind of need to be clamped, or we need to modify our fill rules, but I don't know if we may have to actually just clamp these most of the time. That's not actually a problem for us. We can keep going, I think, if that makes sense. I don't think there's any real problem with that, right? But because it's not actually going to fetch out of bounds if the U is slightly over. But yeah, we're going to have to figure out how you want to handle that. In SIMD, it'll be pretty easy for us to clamp those, so it's not really a huge deal, but yeah. All right, so if we're in here, what I wanted to do was go ahead and correct this stuff. What's the illegal indirection? There we go. So that we're actually doing something that's the same size everywhere, like so. And then I wanted to make it bigger so we could see it at a larger scale. And it's going to be slower, obviously, because, again, we're not very optimal, but you can kind of see it going around there. So we've got that happening, and we'd also like to, you know what we should probably do, too, is maybe keep, well, I don't know if we need to do that. We'll save that for a second then. What I'd like to do, too, is make that angle go much more slowly. okay? So I don't know if you can see that well enough on the stream, but you'll notice that it's kind of, I mean, when you kind of look at what's happening in there, right? It's very flickery, and it's not really what we would want, because we're kind of making giant pixels, right? We're actually doing giant pixels at each step of the way, and it kind of makes it so that it's not really taking into account sort of where we might happen to be subpixely, right? And so what I want to do is start to kind of talk about subpixels and subpixel accuracy, which obviously is going to involve a bunch more stuff. So I figured I'll just get us started on that, and then we can kind of I don't know, next week maybe we'll try to solidify most of it. But hopefully you can see, maybe I'll make that even a little bit bigger. Yes, I don't care. So next statement. Maybe make it a little bit bigger, and probably put it in the center of the screen too. I think that might be a good idea. So what I'd like to do here is, when we do this, what I might do is say, okay, the origin of it, I'm going to subtract half the x-axis and half the y-axis from it, so that it remains in the center of the screen, right? We'll just offset it like so, so that we're kind of always looking at it right in that center. And you can, yeah, I mean, I don't know, you can kind of see, we basically just get a ton of aliasing there, right? And that's because we're just drawing pixels and we're looking up those pixels. We also have, and you know what, let me show another thing too. Actually, maybe this is the best. My head is kind of spinning. I wasn't thinking I was going to talk about this today, so I'm kind of thinking like, okay, what should I do? So maybe we'll do one more thing too, before we start spinning this around and doing other stuff like that. Maybe what we'll do instead is we'll actually move it along, right? So what we'll do here is we'll say, okay, instead of this stuff, we're not even going to do that, right? We're going to fix that x-axis and the y-axis to just be their respective axes, right? We're not going to do anything fancy with those, right? All we're going to do is do that, and let's see here, that'd be 300, 300, like so. All we're going to do is that. We're not going to change the angle at all. So when we draw the thing, it's just a big tree, right? There's the big tree, and you see it's been magnified, right? Its pixels are all kind of like little rectangles because it's, you know, the bitmap is taller than it is wide, and so that's what happened, right? And what I want to do now is I want to just move this guy slowly, kind of left to right, if that makes sense. So I'm going to take this angle value, and I'm going to make another one, right, which is going to be like displacement, right? And I'm going to make displacement be a function of that angle, right? So we'll kind of wobble back and forth 10 pixels to either side. I'll take that displacement and I'll put that displacement in so that it's basically like you know, a displacement sort of horizontally back and forth as the thing goes. Now, what I want you to observe here is sort of the nature of a thing that we've hinted at a bunch of times, and that is that value is continuously moving, right? I mean, the sort of speed at which this thing is going, it's changing every frame its location, but it kind of snaps into place as it moves one pixel over, right? Each time it moves one actual pixel over, you see it shift, but that's all that happens. And furthermore, you can kind of see like wiggliness in here, and maybe if I speed it up just a little bit, so maybe I speed it up just a bit so we can, that motion is a little more exaggerated there, hopefully. Maybe not. Oh, whoops, that's not what I wanted to do. I wanted to speed it up. There we go. So you can kind of see how you get these like lines of motion, how it kind of ripples. And what you're seeing there is the fact that we're stepping through pixels, right? And basically the pixel values will change from one pixel to the next. I'm trying to think of a good way for you to, because like look at this motion, just study it for a second, right? And you see how there are these kind of wavy lines that kind of appear to move through it. So what's happening there, right, is that you have a situation where the number of pixels and number of texels isn't dividing out evenly, right? So what happens is I've got some pixels, right, on the screen, like so, right? And then I've got some texels in the texture map, right, in the thing. You know, these are, we call those texels, they're really just more pixels, right? But pixels are things that are on the screen, and texels are things that are in a texture. We just use that nomenclature to make things clearer. So we've got some pixels, and when we're magnifying stuff like that, one pixel maps to several texels, right? So these texels here all get the same pixel color, right? They all get this. I'm sorry, these pixels all get the same texel color, right? So if this is color A, all of these guys get color A, right? And if this is B, then all of these guys get color B, right? But the problem is when it doesn't divide out perfectly evenly, which it almost never will, then really what happens is as we move through the pixels, a single texel maps to one and some amount, right? It like ends right there, right? So that's the width of the texel mapping, right? And then this next one is going to be exactly as long, but that means it ends a little bit further down. And then finally, this one ends before it actually covers the pixel center. What that means is you will see 3 pixels from this texel, 3 pixels from this texel, and then only 2 pixels potentially from this one, or 4 from this one, depending on how it, it goes out, right? You'd see 2, and then 4, 2, 3, 3, 2, 3, 3, right? You'd see like a pattern, a beat frequency happen as you see those sort of things divide out, and it leads to this really ugly amateur hour thing, which is exactly, unfortunately, what I see in a lot of indie games sometimes. It's really depressing when I see this. And furthermore, you get the even worse artifact, which is you will see this motion as it's moving. It only moves when it can move a whole pixel, right? So you get this sort of stuttery motion, right? That just doesn't look smooth. And you get that, I see that a ton of times. It bothers me at some deep level. You'll see a game and it's got like a parallax background, and the cloud layer in the background is like going, while everything else is updating at 30 frames a second. It's effectively updating at like 5 frames a second because they didn't use subpixel precision for the rendering, right? So that's that, right? That's the situation that goes in there. So what I want to do is start tackling these problems, right? What we want to do is start tackling these problems. And the first thing we can do is at least start to look at whether we're being correct in terms of remembering where we roughly are in pixel space, right? And so the first problem that you will see immediately when you look at the code that I'm writing is this right here, right? Do you see this? We got past floating point accuracy for where the origin is, but you'll notice that because we're looping over pixels, I just flat out ignored it and said whatever the rounded pixel values are, that's where we're at now, right? But that's not really where we were, right? That's not really the location of the thing. That's the location of the pixel. But I sort of semi-redeemed myself, because what I did is I then said, all right, that's the location of the pixel we're on, but I'm going to subtract the actual floating point origin from that, right? This is where we actually were. So if I had just done this and then was using that somehow as the XY coordinates for lookups, that would have been bad. But because we're still doing everything relative to that floating point origin, that restores back in that fractional value that actually lets us know where we actually were, right? And that means that we'll be filling the pixels correctly with the correct fractional measurements as well, so that when we do those edge tests, we're actually testing against edges that are properly moving through that space. So this is the thing that saves us right here. This fact that we're still subtracting in the origin should mean that we at least still have the information that we need. So the question is, though, why do we still look like that, right? And the answer is because we then go ahead and throw away that fractional precision by just doing a round operation here, right? So even though we know where we are fractionally in the texture map, we know specifically that this pixel maps to a very specific place in texture space, right? Like maybe it maps to right there or something like this. Even though we know that, we always just round to whatever the closest pixel is, right? So what we want to do is we want to do something that does a better job, basically, of figuring out where we are in the texture map so that we can produce results that are subpixel accurate. And so let's talk about how we're going to do that. All right. So what we want to do, we've got our texels, right? And what we want to do is say, okay, we've got a particular pixel, and we know the location of that pixel in the texture exactly, because we're computing it all in floating point space. So, here's the center of the texel, let's say, right, like so. Here's the center of the texel, and we now have, sort of 4 pixels that are kind of creating a space around where we want to sample. And so what we're doing right now is we're just taking this pixel's color and we're using this pixel's color. And what we'd rather do is we'd rather lean on a linear blend, right? That linear blend that we've used so many times. What we want to do is leverage that linear blend to produce a color that will allow us to smoothly sample the texture anywhere in this rectangle, right? We want to be able to say, okay, we know 4 color values, so if you want something that's in between them, let's just blend those colors together so that we can produce a reasonable result, right? Does that make sense? So let's say we're going to do that, right? If we're going to do that, all we would have to do is load these values and then blend between them using the linear blends we already know how to do, right? So let's say we have, A, B, C, D, right? So this is our blending thing here. We've got A, B, C, D. Well, you already know how to blend between 2 of these, right? So if we have a pixel that's here, right? You already know that if you take the number between 0 and 1, we can do the linear blend, right? The equation I say handles just about everything, right? Plus, wow, that's the worst drawing of that equation. Plus TB, right? This equals the value. That's the sampled value. That's like the AB blend, right? So all we need to do is produce that T value, and we could blend between A and B. And similarly, we would also know how far we would go there. We would know how to produce the C and D blend, right? So we know how to do that linear blend, or a lerp, as it were, right? We know how to do a lerp between A and B, and we know how to do a lerp between C and D, right? But what we don't know how to do is do a blend between A, B, C, and D. And the answer is you just do the lerp again. Once I produce the blended value of C and D and A and B, then effectively I've created 2 new points along the border. And so if I want a point here, all I would need to know is some other blend that tells me how far vertically to blend the 2, and then just use those 2. So what I can do is I can actually compose lerp on top of itself, right? And I say lerp between the result of these 2 other lerps, because all I'm doing is producing 2 new points that now form a line that I can lerp between. So all we really need to know is we really need to know a fractional value this way and a fractional value this way that goes between 0 and 1 that tells us how close we are to each of the texels, like an fx and an fy, right? And guess what? We know exactly what that is because when we were actually computing the u and v, we didn't have to round it here, right? We had the value. So let's do it this way, right? Let's do our texel x, like so, right? There's our texel x and our texel y, right? Those are floating point values. Once I round them, it's free for me to reconstruct the fractional portion because I can just say whatever the rounded value is, the real version that I had before that had the fractional part in it, if I subtract away whatever the part is that I came up with the rounding, should give me that fractional value that was left over, right? So I already know what I would need to do to blend, right? Really, really straightforward to do that blend, right? So let's just do that. I mean, let's just blend those colors, right? Not particularly hard. So I've got this texel fetch here, right? And all I need to do now is do that texel fetch. I just need to do that texel fetch for 4 things, right? So I've got like, like this. And in fact, I'll use the ABC that I did before, right? If I fetch 4 texels, it's just the texel pointer, right? With a few additions, right, to it. The first one we sample right out of the texel pointer. The next one we sample out of the texel pointer plus 1 pixel, right? The next one we do plus the pitch, so we're on the next row, right? And then the final one we just do with the texture of the pitch plus 1 pixel, so 1 x and y. And there's our 4 texels, right? Does that make sense? Pretty straightforward. Now the problem is, when we do that, we may fetch off the edge of the texture map, right? So what I'm going to do synthetically, just for the moment, again, this is not going to be probably the final way that we would handle this, but what I'm going to do just for the moment is I'm going to pretend our texture is smaller than it actually is, okay? So what I'm going to do is I'm going to pretend that the width is 2 less than it actually is, and then I'm going to add 1 at the beginning. So that way we're always kind of in a rectangle that's a little bit smaller. Does that make sense? Hopefully that makes some sense. So then in here, I'll just use texel A for now, like so. And so you can see we're still getting the exact same results, which is what we want. And so now all we have to do is blend these guys together to get our final result. So if I want to do that, I believe I finally did add that linear blend. Of course, I've got to actually, I guess I have to actually loft out the values as well, which is a bit of a pain. But let's go ahead and do that. So this is texel pointer A, actually, texel pointer B, texel pointer C, texel pointer D, right? So if I actually want to do these, I need to actually do this thing where we actually extract the color values out, if that makes sense. And so what I need to do is something here where we actually take, so this is doing the pre-multiplied alpha as well, sort of baked in there, right? Which we don't actually, yeah, okay, well, let's rearrange this. So if I wanted to do this, this is kind of getting into some things that maybe we didn't want to get into yet, but so if we do this sort of operation and we need to pre-multiply our texture values, we'd rather have pre-multiplied them in the actual texture. And unfortunately, we haven't done that yet. Oh wait, no, I take it back. That's just pre-multiplying by the color that's coming in. Totally fine, never mind. We're good here, no problem. So what I probably will do is I'm gonna take this out for now, so we're not gonna use that color A at the moment, and I'll do color A. All right, so if I want to read out of this texture, and I'm going to go ahead and put in my values here. So there's red, green, blue, and alpha. There's my texel A, right? We've extracted the values of it out and gotten those. Then I'm going to go in here and get the rest of my values. So there's texel B, texel C, texel D, and then I'll just do pointer A. Probably should have done that before I cut and pasted, but you know how it is sometimes, right? Like so. All right, so we've got our A's, here's our B's, here's our C's, here's our D's. So now we have all the texels, and all we have to do is actually lerp between them. And then when we have our SA, when we did our SA, our SB, or that stuff, we can actually just still do those the same way we were doing them before. All right, so this will just be, our final texel values are our final texel values. There we go. Just set ourselves up for feeding into that other equation. All right, so right now, if I set it to just be one of our texels, just to verify that we were reading them right, let's see here, V4 texel, right? In theory, this should give us all the values that we need. We should see the same tree. We do. So now all we have to do is produce this texel by properly doing that linear interpolation. And so I said we need to compose the lerp. So here's our lerp. There we go. We need to do texel A and texel B. We need to do a lerp of that with texel C and texel D, right? And again, we've got our fractional y that lerps between those and our fractional x that lerps between these. And that should put us within striking distance of actually doing that texture filtering. So what is the problem here? V4. Oh, right. We don't have a version for this for V4 operations, it looks like. And so I will manufacture one. So really, lerp is the same no matter what you're doing, right? So you can change it to anything else. Again, if you're a template style person, this is a place you could do templates there. Should work fine, I would suspect. Let's see here. And we don't have multiplication for those as well. So scalar multiply, we just want that as well. Let's see, V3 operations, I guess we'll probably want all of these. So yeah, if you're doing templates, you should be able to just use templates for these guys. There shouldn't be a problem with that. I'm going to go ahead and, I just don't like using templates. I find that it's just, they're always a headache, so I stay away from them. If you're using JAI, if I was using JAI, obviously that is the preferred solution, and I wish we were, but we're not. So we got to suffer through for a little bit longer. We got to suffer through with C++ for a little bit longer, but hopefully not too much longer. John, if you're listening, not too much longer, right? There's going to be a JAI distribution that we all get to use, right? And it's awesome. I'm sure he is producing it as we speak. Okay. Yeah, so that looks like pretty much all we would need to do there. So off we go. So what's the problem? What are we missing? Oh, the lerp is before. We need to put that afterwards so it can access those functions. And there we go. All right, so now we've got our properly blurry, although why, of course, it stopped moving, which doesn't seem like a good idea. I don't know why it stopped moving. That's not a good sign. Let me go ahead and, all right. So I don't know what I accidentally did to stop our poor tree from moving anywhere. Oh, there, you know what? It actually is moving. It's just our stuff is subpixel now, so you couldn't see it. Because it's so smooth, you can't see the wavy lines. It actually was moving. So that's, okay, that was pretty funny. So as you can see, that helps a lot too, just with the change in the size. Let me go ahead and show you maybe with a little bit more. I mean, you can see how different that was, right? I thought the thing had stopped moving. That's how smooth it moves now. Once you start to put that sampling in there, you can't even see it anymore. It totally fools your eye. And we're not even taking as much care as we should in a lot of places. So I suspect we've still got stuff we can do to make it even better than that. But let's go ahead and make that a little bit more pronounced maybe. So now you can see it moving, right? And we're still, there's still a choppiness there in terms of where it is. So I think we've still got some problem, although that may just be our frame rate. So what I could do is say, let's go ahead and make it a little smaller, because since we're not optimized at the moment, our frame rate is definitely, oops, that's the wrong place. Our frame rate is definitely an issue. So yeah. So there's our moving dude, right? And do you see how nice and smooth that is? In fact, you can basically see right now that only our edges are a little bit unsmooth. You can kind of see them being a little unsmooth there. And so we can talk about some reasons why that is and maybe fix that a little bit. But I don't know if you can see how nice and smoothly that guy moves by comparison to the old guy. Just for comparison purposes, if I was to go back to using the old way, which is to do this, right? So let's go ahead and compare those two, right? So here we have it moving back and forth, and now I'm going to take it out so it's moving in the sort of, well, no, I'm not, because I made a compile error. So this is the guy moving in the old way, right? And you can kind of see, like, once he's getting moving at full speed, he shimmers a bit, which is objectionable, but he doesn't stutter that much. But when he gets to the end, he's very stuttery, right? He gets that kind of really sort of stuttery motion at the end. Whereas when we do it with the nice smooth version, he doesn't wave when he's moving, and when he glides nicely to a stop without you ever seeing that sort of pixel stuttery motion. Let me see if I can make him just a little bit bigger so you can kind of see a little bit more of that. Well, our frame rate is just too bad at the moment is the problem. So I don't know, we're going to have to do some optimization before we can probably actually show what it looks like when you make it a little bit larger. That's unfortunate. But there you can kind of see it too. So let me go ahead and I'll switch it back to the pixelated version. So you can see all that crawling that's happening in there. And do you see that stuttering at the end, how ugly that looks? And again, it might be hard for you to see with the video compression too, because the video compression adds as a smoother. But yeah, there you go. So yeah, we've got a bunch of work to do. We're far from the finish line on rendering, but hopefully you can see hopefully you can see that we're already pretty well on our way there to having a renderer. I mean, that's the primitive that we need, which is textured filled quad. So we've kind of got we kind of set ourselves up for next week to really kind of get down to it, right? And of course, I also should probably put a thing here that says to do Casey formalize texture boundaries or something like this, just so we don't forget about that. All right, so we're about out of time anyway. So maybe it is time to go to that Q&A. So let's go ahead and do that. And we'll leave our little tree. In fact, you know what we should do too? I think we should get our tree spinning again, probably, right? That seems like a good idea to me, just so we can see what happens there as well. So there's our spinning version of the tree. You can see it's going there. And the spinning version of the tree, we would also like to check that out in both cases. So let's see here. Here's our lerp version, right? So you can see how ugly that looks when we rotate it, right? You can see how ugly that all looks. And when you go to the lerped version already, it just cleans so much of that up. You get rid of so much artifacting there. And so that's, by the way, just so everyone knows too, that's called, when you're doing texturing, that's what they talk about when they talk about texture filtering. And so, like, for example, if you talk about linear texture filtering, that's what we're doing right now. Anisotropic texture filtering is related, but does some more stuff. MipMap-based filtering does more stuff as well. So there's other levels of filtering you can start adding in there. And right now we're doing the most basic one, which is like a simple bilinear filter on the texture so that we can produce a smooth result instead of a hard-edged result on those pixel boundaries. Niblo, will the wall trees be subpixel accurate now? So you should be able to answer that yourself, my friend. Should they be subpixel accurate or not? And of course the answer is no, because we're not calling this routine to draw them, right? So until we actually call the routine to draw, like, remember, this is only draw, there were only one place that calls draw rectangle slowly. So these guys are still going through the old draw bitmap path. So until we get this nice and fast and accurate and everything is good, and we're ready to actually call everyone to go through it, everything else will not be subpixel accurate. So you can see that the head is not subpixel accurate at the moment, right? The top of the tree seems to be cut short. That's correct. Why do you think that might be? Do you have any guesses? I will give you a hint. Although it could actually just be, but oops. I did not mean to do that. What did I do? No, don't edit the code in here. While we may have other bugs in there as well, and I don't actually know, remember that this guy, right, is part of the problem. Oh, and you know what I forgot to do? We're bilinearly filtering now, so we don't want to round. So we had two reasons that the tree was cut off. One is because we actually do cut off the top and the sides, right? Because we're just arbitrarily only using one pixel in from everywhere. But the other reason is we shouldn't be adding 0.05 anymore, because we're doing bilinear filtering, so we don't want to round, we want to floor, because we're using both sides, right? So yeah, so we can get a little bit of that back already just by getting rid of that 0.5, but only a little bit. There's another part of it which has nothing to do with that. So if we get rid of that 0.5, which we should have done, you can see we get a little bit of the tree top back in. But also remember that tree top, I think that's just the last piece of it right there. So I believe that is just because, like, I think we're also cutting this edge of it as well, if that makes any sense. But I'm not totally sure about that. So for example, if right here we were to let it go further, right? We'd potentially fetch outside the texture, but that would bring it back inside, right? So you can see more of the treetop, but now we occasionally fetch outside the texture. So, yeah. Is tree spinning going to be in the DLC? No, that'll probably be, well, it might be day one DLC. Like, obviously people shouldn't be able to just get a spinning tree. They should have to pay extra for it. So, but I want it to be there at the beginning of the, right from the first time you play the game. So maybe it'll be day 0 DLC. Does it rotate with subpixel accuracy? Yes, it does. Although, again, we've got more stuff to do before we can really say we're subpixel accurate, because we haven't really gone through and analyzed everything properly yet. So yes, we are rotating with subpixel accuracy now. And you can kind of see that too. You can see how smooth this looks in here, right? Because, for example, if I stopped moving it side to side, for example, so let's say we go in here and we get rid of this disp, right? So we're not moving it back and forth anymore. So if we get rid of that, you can see how smooth that looks in there, right? It's super smooth, right? You don't see any real artifacting in there. And we're turning very slowly, so you can see that we've got a nice subpixel thing going on there. But again, we've got more work to do, and we have to do some work for the texture boundaries as well, like I said, so that we don't have that tree clipping problem, and there's a bunch of other things, but again, those are polished things. What's the most major fundamental thing left to do on the renderer? Well, performance. I mean, that's the thing, right? It's fine and good to get a nice little spinning tree here, right? But if we now need to draw the whole screen using this sort of technique, and we want it to be fast, and we want it to be capable of doing overdraw and that sort of stuff, that's really the next major obstacle that we have. Now, again, we don't really have to be that fast for shipping, because like I said, we'll support the hardware path, and I guess you could say that's the other major thing left to do is the OpenGL version, but I don't know when we want to do that. Like, it depends on how fast our software rasterizer ends up being, because maybe we'll just use our software rasterizer for a while, but and we also have to figure out what we want to do about clamping. And I'm not sure. I think we just want to actually do the clamping for those guys, but I'll have to think about that. How would you do smooth subpixel rendering for something like pixel art graphics that doesn't blur but still moves smoothly? So the way that you want to do that, it's a little complicated. I mean, it depends on what you're doing, right? So how can I explain this? Let's go to the blackboard. It's a good question. I'll start with that. So this is more of a technique question, so I'll just explain to you what's happening, and then you can think about the technique yourself. I can give an example of one solution, but it's not a problem that I've ever had because I don't really do pixel graphic stuff, so I can't say definitively that I have a solution that I like because I'm just coming up with this on the spot, but I can tell you the nature of the problem. So the nature of the problem is as follows. Suppose you have a texture map from a pixel sprite, and these pixels are meant to be big on the screen, right? So when we're talking on the screen, you know, we've got our nice 4K display or whatever, right? And so in good times, it would just fill, like one of these pixels would fill like this whole thing, right? So here's A, and this whole thing is A, right? And then here's B if it was aligned, here's B, right? There's B, and it's all good. And so the problem now is what happens when this moves to the side, right? When this moves to the side, so you can imagine, in fact, I probably drew that poorly. Let me draw that a little bit better. So here's A, here's B, right? So now we start off and we've got A and B are here and here, right? So here's B and here's A. If they fell perfectly on a pixel boundary, then everything's good. But let's suppose that they don't. So let's suppose that we now have it, right? So we've got something more like this, right? Same size still, but they're just off a little bit. So here's B and here's A, right? So what I want to illustrate here is if we were to do what we were doing, right? If you were to do pure linear filtering, then what would happen is you would destroy the good case, right? Which is where you have this nice solid A and this nice solid B. You would destroy that case because it would blend the whole blend, right? So all these pixels, all of these would all be blend, and you would not see those nice hard pixel boundaries that you want with the pixel art. But at the same time, you've got a case here where these two pixels, you really do wish these two pixels would blend, right? You don't want these guys to blend, but you want these two.
So really what you want to do here is you want to say, okay, if a particular pixel would have landed in if the nearest neighbor sample for a pixel on either side of the pixel would have landed in either in two different pixels, then blend them, but otherwise don't. And you could actually do that in a pixel shader if you wanted to. That's totally doable, and you could explicitly write that. So that's the perfect solution, right? Would be to explicitly write it that way. Another solution is multi-sample, right? Turn on MSAA and turn off linear filtering. And then it would actually be the case that these staggered pixels would pick up the fact that one was coming from either or, right? So that's solution number 2. So here's solution number 1, right into pixel shader. 2, MSAA. 3 is by far the poor man's solution, which is oftentimes the best one because it runs on the most platforms, and that is manual pre-upsampling, right? So what you do there is you say, you know what? Okay, so the artist handed me this little 4x4 pixel sprite or something, right? And there's the A and B up in the corner. And the problem is when we're doing linear sampling, right? If I was to turn on linear, then like this pixel shows up as being a third of A, and I'm sorry, a seventh of A and a third of B. And that's not what I want. I want it to be like solidly A. All you do is you just upsample that, right? Pre-make a texture that's huge, right? This 4x4 texture, make this into a 512 by 512 texture where all of these are all A. A, B, 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 B. So most of the time, it is picking between two A's, which just produces the color A, and only when you get near the boundary of A and B do you actually produce B, right? And that's a really cheap way to do it. So what I would say is if you're working with an engine and you don't have any control over it, you don't want to be fancy, because this burns a lot of texture memory, right? It burns a ton of texture memory. But texture memory is pretty cheap nowadays, especially for a pixel art game, because there's just not that much art. So all you have to do is blow those art assets up by actually just replicating it. So take this 4x4 and spam it out into a 512 by 512, where each pixel, you take 512 divided by 4, right, and you get 128. So each pixel now maps to a 128 by 128 block of the same color, right? And that'll solve your subpixel problem. Just not as perfectly. Couldn't you use the rounding and truncate to not sample outside the edges of the texture? So the problem is really just we have to have a relatively sane scheme for how we're going to do this. This is an accuracy issue. So if you think about how this works, right? Technically, we're always doing a truncation and then we're adding one. So like if we wanted to be 100% explicit here, we don't need the +1, right? And we need to just make sure that we're 1 away from the end so that when we do this addition, we always make sure that we're within the boundary, right? So I think that's the minimal one we could do. Again, I'd like to go over this a little more carefully, but I think that's the minimum that we could do. And, I mean, that looks pretty reasonable. It looks like that top of that tree is back now for the most part, right? But again, that's just stuff we want to analyze a little bit later because we didn't really have time to kind of like work it through. And I didn't want to just start going, oh, well, we can do this and that. So I'd rather sort of take it a little bit slower. But yeah, that's the basics of it, right? Why are you still adding 0.5 to tx and ty? So I'm assuming that question got asked before I did that. Is it any faster if you just test the domain of UV instead of testing edges? So the way that we're actually going to do this when we're doing performance, I think Here's what I'll say. I don't often write software rasterizer stuff, right? So I don't want to answer incorrectly because it's not really my field of expertise. But I guess what I would say is I believe that the way that I suspect we'll finally do this when we actually write the optimized version, which is like what we're kind of getting to, I believe you could say that that sort of is what we will be doing. We won't necessarily be thinking of them as much in terms of u and v. We'll be thinking of them as barycentric coordinates. Let me just make sure that that's just the same clamping thing. Yeah. So like, I think what I would say is yes. I believe that's the way you do it quickly. Is that because you're looking at the barycentric coordinates and you're testing the same coordinates that you're using for lookup. So I don't know if the answer is technically yes in the way that I've structured it, but I think it will. I think you will see that that ends up being basically what we do, because you will, like, we want to collapse both our lookup and our edge functions into the same parameter space. So I think the answer is yes, is I guess what I would say. But don't quote me on that because we'll have to see when we actually get there. It's not something that I write often, and so I'm not prepared to say definitively yes. Software rasterization is like way out of my expertise area. Like, this is not what I do on a daily basis, right? So I'm not necessarily qualified to give pat answers to things like that. Is rendering on the CPU different in comparison to rendering on a GPU code-wise? Not really. So basically, the difference between the two is this loop. So the fact that we're implementing this loop is mostly the difference. The stuff that happens inside the loop is the shader. Like, we will be writing shader code in the GL version that does exactly the same things that we do in here, right? So basically what happens on the GPU is the GPU does the rasterization part because it's built in. So you don't control that, unfortunately. So it wrote this part, right? And then you do a lot of this stuff. And some of it you can have, some of it's got like macroed up for you. So like you don't have to manually compute the U and V's, it'll compute them for you sometimes and stuff like that, right? Like there's things you can do, like the lookups, like the TXTY, I mean. It's got a texture unit that can do that too. So a bunch of things are macroed, but it's all the exact same stuff, which is why I'm going through it with you this way so that you can see, okay, everything, now you know what the GPU is doing. Like the GPU is doing this code. It's doing much more higher end versions of this code, right? Because they, keep cranking on it and trying to do more and more optimal things that do like, hierarchical culling and all these sorts of things. But they're basically doing exactly what we're doing now. Are there performance benefits for using a quad as primitive over triangles in a software renderer like this? Yes. Excuse me. I don't want to overstate the case, potentially, but there's actually performance benefits for using a quad as a primitive in hardware as well. Like basically, the only reason they don't do exactly what I'm doing here and do it as quads is because quads don't work as well in 3D because triangles are the actual primitive that can construct everything. Whereas in a sprite engine, quads are the things. You never have a triangular problem. And that gets down to the fact that surfaces, have extraordinary vertices and triangles are the only things that can properly tile and all these other sorts of weird things like that. And that the plane equation is only defined on a triangle and all this sorts of stuff. So there's all these reasons why they go triangular. But at the rasterization level, if you're a sprite engine, even if you were a hardware sprite engine, I would be willing to say that I suspect the hardware would always be much faster if it was quads than if it was triangles, because it'd be half the throughput, right? So yeah. Why do the edges of the tree look like they are feathered? It's because they actually are. So if you take a look at the actual art assets, if we go into here, So where are the art assets? I guess this is it. So if we take a look at the actual assets, you can see that they actually are feathered. So I'll create so you can kind of see a white background. So do you see that? That's how they're actually made. So that's just how that is. Let's see. Where's the yeah. Will the different renderers be in the platform layer? No, because they're platform independent most of the time. So there'll be sort of a different thing for renderers where we'll kind of we'll pull them out once it's time to do that. We'll pull them out into that third tier. I've talked about multiple times, I said we're going to have a 3-tier thing. So. I saw a great video on YouTube called Computer Color is Broken from Minute Physics that talks about how blending colors is usually incorrectly done. Without relying on third-party libraries, you have an opportunity to do it correctly. Yeah, so we will be doing it correctly, or close to correctly. You don't really need to do it. So they're talking about situations probably that are a little more important than the ones that we're talking about. So like if you're doing a physically based lighting model, you typically have to take it into account. If you're doing high dynamic range, you have to take it into account. If you're doing sprites like this, you don't really have to take it into account, although your edges may look a little bit better. So like the edge blending may improve. So normally I would not advocate, the thing that they're probably talking about in that video is gamma. And normally I would not advocate correcting for the gamma in a sprite engine unless you had a really good reason. But because Juan Chun made me promise to show people how to do correct gamma, we will be doing correct gamma because of Juan. And so you will see me when we go into our sort of optimization paths and we have SSE in there when we can actually start to do it without it being impossibly slow. I will show how to do the gamma correction and, you know, you can see what the results are. They're not particularly impressive, but they're a little bit better potentially, maybe. Again, really it's for Juan. Juan made me promise to show how to do it, so I will do it. Basically, it just involves squaring and then square rooting or using a color table lookup. It's not rocket science. Remember when you introduced render group the other week? Is this subpixel rendering lerp one of the things that will go in the render group? Dude, it's already in the render group, right? Draw rectangle slowly gets called from inside the render group, right? Draw rectangle slowly is the lerp call. Here is the render group. So I'm not sure what you mean by that. It is in the coordinate system, our little sort of debug thing that we were using here. If you're asking whether the rest of render group will start using it, yes. Obviously, that's what we're sort of aiming towards, but we just got to get it all working in like a little simple debug case so that we can get it correct, and then we can go ahead and have everybody call it, and so that our renderer can all go through like a nice, you know, useful path. All right. I think we are at time, so I am going to call it for today. Man, 2 days back to back where like nothing went wrong with rendering. I guess it just goes to show you that programming visual stuff is easier than programming non-visual stuff or something. Let's go ahead and save off our mischief there. But yeah, thank you everyone for joining me for another episode of Handmade Hero. We did linear blended texture mapping today and it all went great. Yeah, what can I say? That's a lot easier. I had it in my head. I was like, the renderer is going to take like 2 months. I think I even said something like that. And yet it really took a week for us to implement mostly all the features. And so I guess we'll next week we'll work on tightening up the math. And then the week after that, we'll start working on optimization. I don't know. At this point, who knows? Like, maybe we'll be done by the end of next week. I don't even know what to say. I thought software rendering was going to be a big topic. It just doesn't seem to be. And so, hey, that's great. I mean, the sooner we get to making the game, the more fun we can have making the game. I don't know, but I love making renderer stuff, so 6.5 doesn't the other to me. I guess I'm just happy that it's going smoothly. So I hope you guys are enjoying it. I know I am. Next week, we'll tighten up the math a bit. I want to go through there and start to talk about like pixel centers, fill rules, barycentric coordinates, and probably some color stuff. Maybe we'll get the gamma in there as well, and then try to get all of that into next week, so we kind of have like, this is the definitive kind of math that we want to be doing, so that we can start moving on to the optimization path, which is really just dropping it down to SSE and making sure that we're doing a relatively minimal number of pixel tests and operations inside those pixels. So yeah, that's software rendering in a nutshell, and that's the path we're taking. So I hope to see you back here next week. Probably should be same schedule as this week, so 5 p.m. Weeknights, right here on Twitch. If you want to follow along at home, of course, you can pre-order the game on handmadehero.org, and it comes with a source code every night. You can download it and play around with the stuff that we're playing around with. It's a great way to learn. We also have a forum to ask questions, and that has ports to Mac and Linux and an annotated episode guide for catching up on old episodes. It's pretty awesome. We have a Patreon page if you want to support this video series, if you enjoyed it and want to support it. That's a really awesome thing we very much appreciate. And we also have a schedule tweeting bot thing that will tweet the schedule at you if you want to know when there's going to be a live broadcast. That will tell you. So definitely check those out when you get a chance. And I guess have a fantastic weekend. I can't seem to get to the taskbar for some reason. There it is. So yeah, have a fantastic weekend, and I will hopefully see you guys on Monday. Take it easy, everyone.